technology could help us to reach also economies of scale to valorize these kind of biomass. And there we could look, or we should look, in anaerobic digestion. Anaerobic digestion is able to treat a lot of different types of biomasses or biowaste and to make biogas, the methane, out of it. And here we have the possibility, and there we are going now, is the opportunity to block the final stage in this anaerobic digestion and to recover, let's say, volatile fatty acids from this biomass, which can be used, which I will show you later, for different applications. So here we started, only to have an idea. So landfilling is forbidden. You can make composting, then you get fertilizers, you can get bioenergy as a biogas, and the digestate is also composted to get fertilizers. And our goal is to get a material upcycling. And as I've seen in the participants, also Philip is here. He was a little bit the brain behind our project Volatile, which was created to get upcycling, material upcycling from biomass or bio-waste. So what we did there is working on anaerobic digestion to modify the parameters to get the possibility to recover so-called volatile fatty acids, which we were then using as carbon sources for other applications. As we were making biomaterials, PHAs, it's a biopolymer. We were working on single cell oil, also to get feedstock for oleochemical industry. And we were also working on so-called omega-3 fatty acids to produce feed or food ingredients in this way. Nevertheless, we know that beside the technological developments, important is also to look how the society will respond to these kind of developments. So we work there on so-called agent-based modeling to look how different factors affect not only a specific part of the value chain, how this affects the whole system to produce. And then we now also standardization is very important, but there will not go so much in detail, as Jochen will afterwards speak about that. So we were working also on some guidelines how to implement such a value chain. So what we did in this project Volatile in Horizon 2020 is we pooled together 21 partners. Important there is the major part, 7 SMEs, 8 industry partners. There were waste treatment facilities inside. There were wastewater treatment facilities inside, all of them with anaerobic digestion, because that would be the starting point. And we developed with them a prototype, which was then implemented or tested in the Netherlands. Here, that you get an idea, as we did it not we started at lab, but we didn't stop there. So we created in the project Volatile a 5 cubic meter reactor, a test system, which was then installed, as you can see here, on a real anaerobic, because it is thought as an additional step in waste treatment. So it was really connected to this anaerobic digestion reactor, so that we were using biomass from real bio-waste in the Netherlands at our partner Twente. And then we produced there, it was, I would also like to mention that was during the Corona pandemic, so it was quite difficult to get access to the test site, but we were able to implement everything, and we were running our reactor there, and we recovered these volatile fatty acids, which was then used as carbon source for fermentation purposes. Here we have to take into account that normally industrial fermentations you use sugar grade, food grade sugars as carbon source. So that means they are in competition with the normal food production, which will be more critical in the future So it would be better if we can provide another carbon source coming from side stream valorization. Here that you have an idea, so we were able to valorize. That was done yeast fermentation. We made single cell oil, and this was then transformed in a soap. So that's possible. So it's possible to use in oleochemical applications. We were able to make biopolymers, PHAs in this case, which are very useful for film applications. So this is a possibility if you're thinking about waste bags or whatever. Also waste transformed in waste bags to collect later on waste again. And then we were also able to use microalgae, heterotrophic microalgae, to make omega-3 rich oil in this context. So this is possible. These valorization schemes are working. If you would like to have that a little bit more in detail, on our publication server of TECNALIA, there's an ebook where the different steps are described quite nicely. So there you get also the contacts to the different partners which were responsible to this. So if somebody is interested, this ebook is there available on our publication server. Okay, based on this volatile project that was working with wet anaerobic digestion, in this case, we were following and the original system of OWS, now Dranko, is in reality dry anaerobic digestion of municipal biowaste. So we were shifting in the project CAFIPLA to a dry anaerobic digestion system, and we were testing different, also more applications. For example, producing caproic acids, again improving knowledge in our PHAs, microbial protein, and we were introducing another step to recover more materials called fibers. Also in this case, fibers, because you're retaining fiber-rich fraction after the preliminary anaerobic fermentation. Yeah, that's what I explained already a little bit. So we were pulling also here to do working on selecting properly the waste streams. Some were going to a separate lactic acid fermentation. Then we had our dry anaerobic fermentation to make volatile fatty acids or short chain carboxylic acids, as we call it there. We extracted fibers afterwards from the digestate using natural diepoektectic solvents. And then we were testing them or showing the applicability of these kind of products from our reactor. I don't want to go there so much in detail because later on you will get the real information on the real experiences from Marie-Aline. She will speak really about the operation of our bioreactor. Okay, so that means
final minute, please.
Okay, I'm on that. So that means we were including not only the recovery of these volatile fatty acids or short chain carboxylic acids, we were also including question of fibers, which can be, for example, very nicely used in materials and construction. There we were making several test trials, and that it's possible. So it should be integrated in a value chain. Also first recovery of volatile fatty acids, biogas potential is still there of the residues, and we can make then the final composting towards fertilizers. Here, as I said, I will not go so much in detail, but that was our 2 cubic meter CAFIPLA pilot, where Marie-Aline will give more information. It's only that you get, again, an idea. It's not lab scale what we were doing there. We were really operating it, also volatile, at a biowaste treatment facility and working, TL5, to put it in a certain way that you get an idea. Somebody said it's bigger, but okay, that's was the objective, to operate that. So then thank you very much for your attention. I hope you had a small overview about these 2 projects which we did. Yeah.
Thank you, Thomas. Thank you very much, and also for being on time. So I think before we move to the next presentation, I think we probably have a minute for a quick question. If you want to use the chat, you need to be quick and type your question, or if you want to be brave and unmute. if there is one question, probably please.
Probably Sonia ask a question on the chat. So probably I just ask a quick question to Thomas. It's great that you also produce, soap and other commodity products out of your biomass stream. So my question is how you can get rid of the waste label out of your products. Is there something Jochen are going to tell us?
Okay. Also, during CAFIPLA, this was really a question. So you need an end of waste. That's correctly. Okay. So you have two options. As the European Commission was preparing for the fertilizer, Marie-Aline knows better than me, but they made a specific end of waste for fertilizers. And their anaerobic digestion inside, etc., etc. So if you follow this a little bit and you compare it to our processes, I'm pretty sure if a company would apply for the end of waste, it would be possible. So if we were doing this exercise during CAFIPLA and comparing what was done for the fertilizers, where the differences of our technology compared to this. This is one option. The other option is, I don't know if you know the company Chaincraft. They are doing this kind of things. They produce caproic acid, butyric acid, etc. They call it food waste, but I spoke to them. In reality, it's subproducts. So the question is, at which point you are taking your raw material, if it was already declared waste, or it's still called like a subproduct. In this case, you don't have that. It's like a fermentation. I take a certain side stream from food production and transform that in volatile fatty acids, for example. So these are the two options. As Marie-Aline has more the problem as municipal biowaste is waste. So there we have to apply for end of waste criteria, but it would be also possible already now to produce these kind of things. Okay.
Okay, wonderful. Thank you very much, Thomas. I think there's already a number of questions on the chat. So in the interest of time, I'm afraid we need to move to the next speaker, but I'm pretty sure that Thomas might have some answers already, and we touch probably end of waste during the first question. So I would like to introduce the second speaker, Jochen Michels from DECHEMA. So Jochen has long experience, over 30 years of project coordinator in the area of renewable resources, biorefinery and bioeconomy. And so Jochen, your 15 minutes, please. You're muted, Jochen. Sorry, you're still muted.
Yes. Okay. I hope fully solve the technical problems here. Yeah. I'm going back to project Volatile, the first Horizon 2020 project Thomas and I made together with many other partners, and we had decided to put some of the results into a CEN Workshop agreement. I will come in more detail to that during my talk, but let me start as ever with what is DECHEMA. Not too much, not to give you a short introduction. So we are a non-profit professional society in Germany, and we think we are the expert network for chemical engineering and biotechnology here in Germany. We just have about 100 employees, but we have over 5,500 individual members. So we can beat TECNALIA in that field a little bit. We have this is our mission, and we have a portfolio, and not to go in more detail, we have a research and project coordination unit, and I'm part of that unit doing project coordination and also some research at DECHEMA, and that's my role also in that project. In Volatile, we have a part of dissemination here, and and CWA is an instrument for bringing results to decision makers, to plant operators, to investors, and also to municipalities. And the target of these CWA is not to go into detail into a certain technology and to bring a certain technology into a standard, but it is the procedure for feasibility assessment. So we put all the information we got during the project together and said, okay, how can you get forward to a decision to introduce or to integrate a volatile fatty acid platform technology in a running anaerobic digestion plant for at least municipal waste. To introduce a little bit what is a CEN or a CEN-ELEC workshop. CEN is, as you know, the European Committee for Standardization, and it is an association of national standardization bodies of 33 European countries. And it is not bound to European Union. Yes, so UK is still a member of this association, and such a workshop is a temporary group. It is open to the participation of any interested parties, and it is somehow common to European projects, and the participants of the beneficiaries of such an European project are getting into this workshop, becoming participants or members of this workshops for the elaboration of such an workshop agreement. And it is completely separate from technical committees, which are responsible for the development of a European standards, but they can be connected if they are thematic near and to such a technical committee. A technical committee can also be part of a workshop itself. Okay. A CEN or CEN-ELEC workshop agreement. In our case, the CWA is a CEN workshop agreement. It is designed with a focus on research and innovation outcomes. It is, as I said, not the full standard, and it should not conflict with a European standard. That will be proven by a secretary. This is one of these members of the Standardization Association. It is a deliverable, and it is developed and agreed by the participants in this temporary working group. And as I said, the stakeholder involvement is limited to those who are interested in the subject, and so it is almost these are almost the beneficiaries of such a project. Yeah, and once published, if a topic shows to be market relevant, the CWA can be is also a source for future standard. In case of our CWA, this is not the case, but it was not really intended to do so. It was just to fix this procedure on giving a feasibility assessment. This was the process long time ago. So just to give an overview of how this is a CWA on its administrative side, you have to make a proposal with a project plan where you describe scope and objectives and some kind of schedule and which resources you need. E.g., it is more that you say that you have all resources on board, especially money to do the job. Then you have you start the workshop with a kickoff meeting where you approve the project plan with the participants and declare the rules of a workshop, declare the chairmanship and also the secretariat. And then several meetings will be conducted to draft and adopt the CWA to its final version. And after approval, it can be publicated. And there are two phases in between where public commenting is allowed and welcomed in this. So if you submit your proposal, there's a public commenting plan on the phase on the project plan, which normally means that it is submitted to the technical committees and they can give a comment on that. And afterwards, the second public commenting phase of a draft consensus is then to the end. And after this 60 days, we had a final meeting where we discussed some of these comments to be included into the CWA. This is the structure of a CWA, and there are many very administrative topics. So I will focus myself on the sections where we put directly input from our results from the Volatile Fatty Acid Platform technology. So in section 5 here is on intention and drivers. So just to give you an impression what we had under consideration for the VFAP technology. So we had these ecologic drivers discussing or arguing that there's no resource conflict and the new bio-based chemicals are produced from waste streams and so on, no negative impact on climate and biodiversity, and pollutions are avoided as much. And there are also social drivers to discuss. It was in that time the circular economy strategy that demands to avoid all waste, and also the obligation on separate collection of waste streams. We found this is a major driver to get more money out of waste collections. And also there is the landfilling of municipal waste has to be reduced to 10%. So there is an obligation to have other uses for municipal waste. And there are also economic drivers we've seen. So from the chemical side, there is a demand to raise the share of bio-based chemicals from 10% to 25%. This was written in the Strategic Innovation Research Agenda of BBI. And personally, I doubt that we will reach out there because for the last 10 years, it was in the European Union about 8%, 8 to 10%, and it did not rise in the last year. But nevertheless, we think new businesses for biogas plants are needed. This is especially true in Germany, where biogas plants are supported for a certain time. And this is about 20 years, and many of these biogas plants are running out of this support, and they need new businesses to run further on. And personally, I think that to upgrade a biogas plant to some kind of biorefinery in a bottom-up approach, this could be very successful. The framework to be considered, we have non-technical aspects and also technical criteria or aspects to discuss in the CWA, and having the non-technical aspects. So we discussed what is in favor of a VFA platform. So it is economics as well as image improvements aspects we had discussed, and we had also put it into the political and regulatory contexts. These regulations are discussed region-specific from the raw material side. So we involved all partner countries of a project to give this discussion on the regulations. And we also developed some kind of multi-criteria decision making tool based on non-technical criteria. And we found 15 criteria that could be grouped into 6 contextual dimensions. I will not go further in detail. You can read it in the CWA because it is still available. And I have on my last slide a download link for it. Yeah, okay. So coming to the technical criteria, this was the biggest section in the CWA. So we discussed a decision, or we developed a decision-making guide on raw materials and the impact of and on current anaerobic digestion plants, the available VFA conversion technology and application of produced VFA. This is something what Thomas mentioned already. Yeah, so looking on the raw materials, we had a look on the substrate quality, covering anaerobic degradability, heavy metal content, organic pollutant content, physical impurities, and variability in substrate composition. And the recommendations we gave in that section were symbolized by traffic lights. So it was very easy to see which of these criteria is in favor for VFA or even not. Then we had a look on the substrate quantity, so how much is available over the year. So is there a chance for a continuous substrate supply? And about logistics, you have to look for the supply chain, transport distance, and so on. And also long-term contracts to get the material for your anaerobic digester. And also these recommendations are symbolized by traffic lights. So yeah, and also we defined the substrate categories for anaerobic digestion. And so we had a deeper look in 10 different substrates for the anaerobic digester and gave a definition and estimate the application potential for these 10 substrates. Okay, and the next section was on the impact of current anaerobic digestion plant. So this means you need skills on microbiological processes because at least VFA production and biogas production show large similarities, but you have to have maybe another process control to optimize the production of VFA in your process. And you have to look on the biogas recovery because if you add the VFA production to the process, that means that hydrogen gas will be produced in excess. And this is a feedback loop to anaerobic digestion, meaning that the VFA are not produced further. So you need to get rid of the hydrogen as well. And you have to look at on the slow degrading organic matter. This may accumulate in the digestate then because the process for producing the VFA is much faster than the complete anaerobic digestion, as you know. Yeah.
Final minute, Jochen, please.
Yes, it is. I'm next to end. Thank you very much. Okay. Okay, and then we discussed also the batch process versus continuous processes, resistance time in the fermenter, maybe necessary pre-treatments, post-treatments, and surface area requirements. This belongs to logistics. So the application, Thomas already introduced that what we did, and we discussed that what can be produced with this platform technology. So I don't discuss this further. And in the last section, we have the assessment methodology to have an assessment to determine if integration of this technology into a biogas plant is economically viable as well as environmental sound. So that means you have to make some SWOT analysis. You have to adopt the life cycle assessment. and then cost analysis and economic feasibility studies. And maybe this can also be backed up by a process modeling as well. So, and having all this information and this assessment methodology, then you can get to a decision to adopt this technology to your anaerobic digester. Yeah, so this is my final slide. Many thanks for your attention. This is the picture. This is really dry stuff, so I have this nice picture in the end. Thomas is available for your questions, like myself. And here you can download the CWA if you are interested in. Yeah, and many thanks for your attention.
Thank you very much, Jochen, for your presentation. Very interesting. So I think we probably have time for one quick question, if there is one from the chat or from the audience. I'll go with the 5 seconds rule. Probably not, but hopefully we get time for more questions in the end. So I'll like to
it is hard stuff,
Jochen.
I know.
And introduce the next.
Yeah, thank you very much.
Speaker. So the next presentation is from Marie-Aline Pierrard. So Marie-Aline has a master in biological science and a PhD in biological sciences and environmental toxicology. And she's currently a project manager at IDELUX Environment in Belgium. Marie-Aline, to you.
Thank you very much. Can you see my full mode screen? Yeah,
yes, perfect.
So, yeah, no need to repeat then who I am. I'm working for the intermunicipal IDELUX environment, and I'm just gonna give you a brief idea of our point of view from the industry point of view. So just very briefly, we are an intermunicipal that is part of a group named IDELUX, and we are located in the south of Belgium. I draw a red line so that you can picture what's the territory we are talking about. And we are just trying to develop this part of the country. So this is about 5 different intermunicipal, and the one I am representing is taking care of the waste. So basically, we are a public non-profit company, and our main mission is just to manage household waste. So basically, the citizen can bring the waste inside the Russie Park, or we collect it in front of the door of the citizen. We also try to educate people on how to sort the waste. And finally, the most interesting part for you is the plants. So the territory we're talking about, as I mentioned, the province of Luxembourg, it's a particular one because there's more trees than inhabitants. So that means from an industrial point of view that we have a lot of logistics to take care about. We have a lot of driving between places, okay? There's not much industries around. Saying that, so we have 2 different plants, and these 2 plants are specifically designed to treat a specific kind of waste. So we have a plant located in Abbé that is really in the south near the country of Luxembourg that treats the residual waste. And then we have another plant, the one that is of interest today, Tinville, who is designed to treat the organic waste. And that's where we have our anaerobic digestion plant. Okay, so there's no interest for us to mix the waste inside the truck, as some people believe, because we have specifically designed tools in each of our plants, and they are really well separated in terms of geography. So about anaerobic digestion, the normal process is that we go up to the final product, which is the methane, to burn it to get electricity and heat. But here in the first project, we decided to stop it at the volatile fatty acids, and then we gave it as new food for some microorganism of industrial interest. So the yeast or the bacteria or the algae, and they were first surviving, feeding on this kind of volatile fatty acids. That's the first point. And then secondly, they were producing something of interest, like the omega-3 or the PHA that can become plastics, which is of interest, of course, for an industrial. So the next project, we wanted to go further because the idea is that it can become something that is replicable for any kind of industry, because you have different kinds of AD plant that are treating different kind of waste, but you also have different environment. As I just show you mine, we are lost in the forest, so there's not much industry around. So the idea was that you could play with some parameters so that you can target specific spectra of your carboxylic acids in this project. So the idea was to come from a current process where you just have the waste inside a fermentator. You have your electricity and your heat because you are interested about that. And then the residue that has no time to be digested goes with green waste, and you do a compost as a fertilizer. And then you go to another process that provides you way more final products potential. So we were thinking that based on what you need, depending on where your plant is located, you would target either lactic acid or caproic acid or macrobioprotein or PHA. And also because you have this dry fraction, you could play with the fibers. And we tried to make some new biocomposite products based on the fibers. And then the residue would go in the what I will call the classic AD plant, so that you still produce your heat and electricity to make your process run, and also your final compost fertilizer. So that was the big idea. So when TECNALIA invited us to write the proposal, the idea, and I'm gonna romance a bit here, okay, because it's more fun. Thomas told me, okay, would you like to join a nice research project? Don't worry, you're gonna receive a nice pilot plan inside a container, and all you have to do is plug it for electricity, bring some organic waste, and that's basically all. Okay, so we were thinking where to put that container so that first it's secure, and secondly it do not disturb our traffic of trucks that goes in and out, and also that it would be close enough from our storage of bio-waste. All right. And then, okay, that was the proposal. And then, of course, there's the challenges, the real projects happening, okay? There was first the pandemic, and then a lot of turnover inside the partners. So that means that a lot of engineers that were present in the beginning, were writing the proposal, were not part of the project anymore when we were running it. So that means a lot of things that had to be challenged. But fortunately, the partners were nice, and we were all working together to reach the same goal. And I mean, it was very constructive. But the challenges, for example, that's the pilot plan that we finally ended up working with. And that means that in case of bringing, for example, 40 kilo per day, that I thought when I was writing the proposal manageable, you know, I could ask one of my colleagues, an operator, to come and just bring some 20 kilo 2 times a day. It's feasible, okay? Because to give you an idea, we are treating 35,000 tons of waste. So when you go so small with so small amount, like 40 kilo per day, then it's even more complicated for us because we do not have the tool for such small amount. So finally, the pilot was requesting 300 kilo per day. And so for sure, my colleague will say no to me. Okay, I'm not gonna bring you 300 kilo by hand. That's a no question. And at the same time, we had to feed the pilot plant at 4-meter height, which is even additional problems because the guy, he will definitely not walk a scale or walk a stair to bring me my 300 kilos per day, okay? So we had to think and challenge ourselves. How are we gonna do that? Because our process is definitely not prepared for that. We are treating tons every day. So finally, we ended up with a tunnel, you know, the rubbish of tunnels that you can have in an apartment, for example, so that you can put the rubbish without taking the stairs all the time, for example. And it was working fine. So that was one of the solutions. And the other solution was to have a second-hand conveyor belt to bring the bio-waste up to the tunnel at 4 meter high. And we built a feed hopper. So we came from a storage hole with nothing, no electricity plugs or anything, no water income, nothing, with a fully equipped pilot plant. And that was challenging, honestly, but we were really happy that we could build that with all the consortium partners. That was really nice team building. So you have the waste. I'm sorry, I'm gonna go a bit quick because I think I prepared too much and for 15 minutes. So you have the organic waste that goes for fermentation, and the residue, the digestate, was of interest for us. And so we had this press, and we had the liquid fraction and the solid fractions. That's exactly the same, it's just different illustrations. So the solid fractions, we would extract the fibers from it, and the liquid fraction, we would filtrate it to ultrafiltration units, and then we would even concentrate it through reverse osmosis. And you can see here we ended up with a black juice, and you can see the fatty oil at the top of the surface. That was the volatile fatty acids or carboxylic acid that we were interested in. So that's the barrels we're producing as much as possible to bring to all the other partners so that they could feed the bacteria to make PHA or the microbial proteins and stuff like that. So of course, running this pilot, we could measure a lot of different things like the pH, the gas production. We could manage to see how the material were going on inside and were mixed up. So a lot of data of interest for the scientists and the research departments who wanted to know exactly what we were playing, what would interact, because when you play with fermentator, you're always playing with a lot of living things, not just one. So it's very tough because when you change one parameter, you change a lot of things inside. So that's very tricky to make some, relations in between. And so we also tried some local waste, what I call the clean waste, because they come from food industry. And also when you add some co-substrate, then you change the spectra of the carboxylic acid you would get. And so that was also of interest to see how it reacted. We tried the pasta waste and the meat waste. And that's the products we got. So the fatty oil, as I explained, but also the plastics. We also try some isolation panels based on the fibers. We combined also the fibers with the plastics that we got from the bacteria, and we made some new biocomposite material. So that was quite nice to show to everybody. Some challenges that we had was specifically the weather, because as I mentioned, we are a municipal solid waste treatment plant, so we are not equipped for scientific researches. So the whole storage where we were working, when it was -10, -12 degrees at the winter, the water just freeze. And we were really scared about the filtration unit system that we rent. So it was really tough. And sometimes I sent a lot of barrels of this black juice that I just showed you. And when it arrived in Spain to TECNALIA or in France or whatever partner who were interested to work with it, sometimes it was just not good anymore because we had no freezer or, we are not equipped for that. And so they could not use it, for example. Same with the fibers. Sometimes I just package it, I don't know, a cubic meter of fibers. I send them to France. And when they arrived there, they was full of fungi, for example. It's kind of things like that you experience and you don't think about it when writing the proposal, for example. So the biggest challenges when you work with organic municipal solid waste as mentioned by Thomas before, the heterogeneous nature, because you're not eating the same thing every day. Your neighbor is not eating the same as you neither. So you don't know what you're going to get. That's the first thing. That's very heterogeneous. Secondly, you have some restriction on the use you can do on the application, because once you use a bin, you have also animal byproducts. So that means you have specific legislation on that, because it's a waste of waste. And it's animal byproducts, so it's even more strict, let's say. And then you have contaminations a lot. You have sorting mistakes. People do not sort all the time perfectly their waste, so it means you have plastics, glass, metals, rocks, and it could be problematic when you go with a high level treatment like reverse osmosis, for example. And that's exactly what happened. So here you can see a zoom on the screw that was mixing the material inside the pilot plant. And you can see that one piece of metal or one rock, we will never know, almost cut into the pilot plant. We were really scared at that time, and we had to stop the machine, just put everything out and start again. And then the other picture, I don't know if you can see it, but we had a contaminant, was this sticky guy who just how you say that in English, plug the pumping system of the reverse osmosis filtration machine. So yeah, that kind of, so it cost us one night work that night with this thing.
Final minute, Marie-Aline, please.
Yes, so we are lucky we have a new funding for a project where we want to focus on the plastics. So we have one project working on the pre-treatment of the organic municipal solid waste when they arrived at our plant. We would like, because most of the waste treatment plant, they have a shredder and a siever. And the problem is when you shred, you sometimes make more pieces of plastics, because the smaller they are, the more difficult it is to remove it. So we would like to try another kind of pre-treatment to compare and see if we can remove more plastics. Then we have one project on the digestate to try to clean it also. And then a final project on the composting system. So really the idea is to remove the contamination. And this one is funded by the FEDER. And so the take-home message, that would be that it's challenging, but if you can do that with raw material like organic municipal solid waste, then you're ready to do with anything else. Because these kind of plants, they are heavily subsidized. They can't economically survive without this help of funding. And the products you got are quite of low value in terms of financial point of view, I mean. So if you can transform it into something that would be more sustainable and with more autonomy, then everything would be really, really a very good opportunity, let's say. So if you have any questions, please feel free to contact me. And thank you very much for your attention.
Thank you, Marie-Aline. Thank you very much for your presentation and for delivering on time. Thank you so much. So we are overrunning already of 1 minute. We can stay a little longer. If there's any quick question we can share with the audience, I think some have been already answered on the chat. We might have time for one quick question or just a few. But before people take the courage and ask the question or type, I want to thank our three guests for today for your presentations. Thank you for your time. I want to thank the Environmental and Biotechnology Network for the support, and of course EPSRC and BBSRC for the financial support of the network and of this initiative. I don't know if there's any.
Luca,
please,
Sonia posted a couple questions, and I think that's the question to Marie-Aline. Is organic MSW really that heterogeneous at scale? And also, if the I think if the AD plant really subsidized at the moment.
Yeah, I can answer that. So
Yeah.
heterogeneous, it's always relative to something else, of course. If you compare to a food industry waste, of course, it's more heterogeneous. And in terms of time, it's true that if you compare all the time the same waste, I mean, from the same territory, it's quite all the time the same. But for example, we have some season peak. I know in my part of Belgium that in January, for example, we are very well producing gas because we have rich waste, because people, they eat a lot of fat, they eat a lot of good things for Christmas time, and then we know that we are going to produce a lot of gas, for example, in January, and we have some peak of H2S2 because of that. And the other question, what about the subsidies? Yeah, we are, because we receive a green certificate when we use the electricity and the heat that has been produced in a green way. And so we receive kind of money based on that. And without that, honestly, I think it's going to be tough. Yeah.
Thank you. And I think there was a question for Thomas at the start. I don't know if you, Thomas, if you can give us an indication of the yields of acids that can be produced, rough indication.
Okay, so this is a little bit tricky, to put it in a way. Okay, one thing is the yield of recovery. The question was, okay, what we did is we separated the solid fraction from the liquid fraction, where we can reach 30 grams per liter of volatile fatty acids. And then in reality, what we did, as it is for the fermentation purposes, we were only getting by filtration rid of other compounds which we didn't want to have. And then we were concentrating the VFEs, because we were implementing fat batch approaches. So that means as higher concentrated the VFEs is, it's better it's later on for the fat batch approaches. So we were trying to reach around 200 grams per liter of VFEs. Okay, I don't have now the real number to say something, but it was not really a recovery that I say, okay, I have 95% of the acetic acid recovered and 80% of the butyric acid or something. I can make the calculations. We have that because we have the initial what is going in the membrane filtration, and then, but it was more cleaning and concentration step than a real recovery in terms of this the specific volatile fatty acids in this case. Yeah.
Okay, thank you very much, Thomas. I think we're already overrunning of 5 minutes. You were probably we should close the session here. So there's been a lot of material going into the chat, so thank you for sharing. Visit the EBNet website for more information, www.ebnet.ac.uk. And you final maybe word for you.
Yeah, just to say again, to echo what Luca already said, a very big thank you to all of our presenters for making their time available to share their research experience with us. And it is really encouraging to see so much interest in this topic. Hopefully, we will have more opportunities to work together more closely in the future. Thank you. Thank you.
Thank you very much for the invitation again, and that we could also share some of our results. So to some of the questions, as at Cordis, there's certain public reports of our 2 projects available. I was just trying to get this as fast as possible, certain things, but it's not the direct link. So you have to go at Cordis at the project and then the results, and they are different of our public reports available. But if you have any question, you can also ask us directly, and then we look what we can share. Yeah, as some companies are involved and working on different aspects also the follow-up, but that can be done. Yeah.
Wonderful. Thank you, Thomas, and again, thank you, Marie-Aline. Thank you, Thomas, and thank you, Jochen, for your time and for your presentations.
Thank you very much.
That's all for today. Thank you.
Okay.
Thank you.
Bye-bye.
Thank you. Bye-bye.
Thank you.
Bye.
Bye-bye.
Bye.